So welcome in everybody to our next N3AS seminar of this summer semester. And today we're pleased to have Joseph Bramante from Queen's University, who will tell us about dark matter in compact stars and galactic structure. So please, Joe, whenever you're ready, take it away.
Okay, great. Thanks very much, Evan, and thanks very much, Anupam, for inviting me to give this talk. I'm really happy to come talk to this network of people who think about neutrinos, nuclear physics, and astrophysics, which are all near and dear to my heart, as you'll see in my talk today. If at any point during this talk you have questions, just feel free to pipe in. I've taken what was a 40-minute talk and slimmed it down, so it should fit the 25 to 30-minute format. And I'm just going to sort of give you an overview of things I think about with respect to dark matter and compact stars. And there are a lot of nice intersections there, but of course I'm not going to go into exorbitant detail. I may have answers to a technical question that you may think about in a backup slide though. So feel free to speak up, and I should be able to see you speaking in the upper right corner of my screen. So hopefully I'll respond. Okay, so today I'll talk about three main topics. Oh, and I should say, yeah, I'm at Queen's University, the McDonald Institute primarily, and then I'm also here today at Perimeter Institute. So that's my background. I spent a good portion of the year there. So today I'm going to talk about three topics. I'm going to go a little bit quickly through the first two, and then spend a little bit more time on the third one, which is a project that I'm actively finishing up right now. So what I'm going to talk about is dark matter that can heat up neutron stars through either hitting them or through annihilation. Then I'm going to talk about asymmetric dark matter that causes neutron stars to implode. This is actually quite an old topic dating back to the late 80s. I'm not going to get much into connections to missing pulsars and FRVs, but you can feel free to ask me about that in the question section if you want to. And the last thing we're going to talk about is white dwarf explosions, and it's from the same kind of asymmetric dark matter or composite dark matter. And I'm going to talk about what connections we can draw between that kind of dark matter and type 1a supernovae, and then even galactic structure, which is kind of like an exciting new frontier for dark matter. So one reason I think neutron stars are really wonderful for thinking about the intersection of dark matter searches, nuclear physics, astrophysics, and even to a lesser extent neutrinos, is that neutron stars can be thought of as nature's dark matter accelerators. So it's the only environment I know of where dark matter is accelerated to speeds that you would expect it to have when it was freezing out of the thermal bath in the early universe. And where it's not just going to get sucked into a black hole immediately. So a neutron star, gets you up to that, semi-relativistic speed, but doesn't get rid of the dark matter. Instead, the dark matter passes through the neutron star. And because the neutron star is so dense, sort of the optically thick cross-section, or the cross-section at which we'd expect dark matter to scatter once with the neutron star, if it has some sort of nucleon scattering cross-section, is about 10 to the minus 45 centimeters squared, which is quite competitive or on par with the sort of sensitivity you think about for a modern direct detection dark matter search. And so something I've thought about with my collaborators in the last 5 years, and we're still developing, is how can I think about dark matter as something that can be sought out using neutron star temperatures. And the concept is pretty simple. Dark matter is accelerated to 0.7 times the speed of light by a typical neutron star. It can deposit both its kinetic energy and annihilation energy if it's a dark matter model that annihilates. But the kinetic energy alone can heat up neutron stars to 1750 Kelvin. And this turns out to be a temperature which is far above the temperature you'd expect the neutron star to have in the late time limit of its thermal evolution. And so just with those small facts, that dark matter can hit the neutron star and heat it up to an observable temperature, you could say, if I were able to find a neutron star near Earth and constrain its temperature to be below 1750 Kelvin, which is the temperature dark matter for the density around Earth and the velocity dispersion around Earth would maximally raise a neutron star to, just through kinetic heating. You could say, what does that translate to in terms of a scattering cross-section? And here I'm showing you the result that we showed. That's a very simple, but in the end, quite accurate, even when you do more detailed studies of neutron star scattering calculations towards that. This shows you what sort of reach you'd expect for dark matter nucleon scattering cross-sections. If you found like a 1750 Kelvin neutron star, that's a bit futuristic at the moment. So is 1000 Kelvin. That's even a bit more futuristic, but it's something you can think about maybe in the next decade as being something we could approach to attaining. And what you're seeing here is that the reach for this in sort of the lower mass limit and the higher mass limit could very well exceed dark matter search experiments. This is for both so-called spin-independent dark matter searches, where the dark matter interacts with all nucleons equally and there's no spin sort of interaction, but it actually equally applies for the spin-dependent interactions. And that's because neutrons are sort of probably free in the neutron star, and so you can scatter with each one of them, and each one of them has its own spin. So this would provide a really nice probe of dark matter models. So after we sort of pointed this out or worked on this, there's been a lot of work since then, and I should say there's also work before us on other aspects of this. Chris Kuvaris, Bertone, Fairbairn being some of the more recent people who've thought about this, but then all the way back to like 1989, you can find people thinking about how dark matter could be sought out using neutron stars, like Itzhak Goldman and Shmuel Nusinov. And it turns out that neutron stars can probe all sorts of dark matter models that are hard for direct detection experiments sometimes to find, including things like muon-Feelic dark matter, because there's a small muon fraction inside the neutron star. That's my favorite little factoid and probe that you can get out of that. But if you think about where we are right now with respect to the temperatures I was quoting before, which is around 2000 Kelvin, we're pretty far away. So the sort of lowest temperature neutron stars, or bounds on neutron star temperatures you can find in a typical review, is sitting at around 10 to the 5 Kelvin. And then within the last few years, there's been an observation by the Hubble Space Telescope of a nearby neutron star that placed a bound for that neutron star temperature to be less than 3 times 10 to the 4 Kelvin. So that's getting closer to the 2000 Kelvin range. But remember that when we talk about temperatures, then if I would think about that in terms of luminosities, it goes like the 4th power of temperature. So this is still 4 orders of magnitude in luminosity away from where we would need to be for this to be a really leading next generation dark matter discovery pathway. However, there are prospects in the next decade where you could use neutron star temperatures for nearby neutron stars, and you could think about using telescopes that are coming online to look for this dark matter heating of neutron stars. I think the best prospects are for things like 30-meter class telescopes, and finding a pulsar within 100 parsecs, or preferably less than 100 parsecs, somewhere between 70 and 100 parsecs would be ideal, and then pointing your telescope at that nearby pulsar. Then you wouldn't necessarily need so much observing time that it would be unrealistic to think about using a 30-meter telescope to look for that. But for the last little bit on neutron star heating by dark matter, what I'll talk to you about right now is one very special kind of dark matter model that you can already use current neutron star temperatures to place a bound on. And that is what we called in this recent work with myself, Bradley Kavanaugh, and Nirmal Raj, subhalo dark matter. And before I tell you what our subhalo dark matter model is, I have to tell you the difference between collisionless accretion, which is the typical accretion you think about when dark matter falls on neutron stars. And that's accretion of the dark matter fluid if it doesn't collide with itself at all. It has no appreciable self-interactions. And I can contrast that with collisional or Bondi accretion. And it turns out that if you think about the sort of impact parameter, gravitational impact parameter of dark matter onto the neutron star, you'll get an extra enhancement of V escape, or the escape velocity of the neutron star, over the velocity dispersion of the dark matter in the halo, VDM here. If you think about collisionless versus collisional accretion. And to derive this, you just need something like angular momentum conservation, or you could do a Sommerfeld treatment of dark matter capture. To calculate this, you have to use fluid equations. But in any case, if you have something like collisional accretion or a fluid that accretes onto the neutron star, then you can get a lot more accretion occurring. So what sort of dark matter model could I reasonably think about where I have actually a substantial amount of interactions between dark matter particles, and I don't run into the problem of thinking about, well, then why didn't the dark matter like flatten? How is it still spherical in the dark matter halo? And the kind of model I can think about where that's the case is subhalo dark matter. And this is where I'd say for some reason, all my dark matter ends up in these small subhalos. We don't really go into the details of exactly that model or model building for this, but probably something like a dissipative dark sector where the dark matter cools in these subhalos is what you'd want to think about. So the very simple model I'm about to show you a plot for is just subhalos of dark matter with a certain subhalo mass m and a certain radius r with just like a constant density in the subhalo. So if I take all the dark matter in the Milky Way galactic halo and I put it into these little subhalos at a fixed radius and a fixed mass, what results can I get? And it turns out that that coldest pulsar that I mentioned before, which has a temperature less than 3 × 10⁴ Kelvin, is enough to put a bound on this kind of dark matter. Essentially, if I think about the parameter space here in the upper plot of the radius of the subhalo versus the mass, then each point in this plot indicates all the subhalos would have a single radius and a single mass, which there would be a distribution, but we're just trying to get a sense of the sensitivity here. So we're using the simplified model. It turns out that in this Orion region here, where this is the subhalo mass and this is its radius, for this parameter space of subhalos, if the dark matter in those subhalos was collisional or accreting like a fluid, then I could already rule out these cross sections I showed you before, which lie well below current dark matter search experiment cross sections. So this parameter space above this black line here could already be ruled out for that very specific dark matter model. So yeah, that's where things stand, and I'm just bringing this up to show you that there's some very special little corner of dark matter parameter space where you can already use the non-observation of neutron star heating to put a bound. Okay, so that brings me to the end of that, and I'm moving a little bit quickly, but the next thing I'm going to talk about that I'm also going to whisk my way through is asymmetric dark matter causing neutron stars to implode. So I talked about dark matter being captured on the neutron star, and we talked about it perhaps annihilating inside the neutron star with other dark matter particles and causing the neutron star to heat up. But let's pause for a moment and think about, okay, if dark matter is asymmetric, meaning for our purposes, it can't annihilate with itself. So it's a particle versus an antiparticle under some symmetry, just like baryonic matter. If that's the case, what happens after it's captured in the neutron star? And what happens is at first, it scatters once and then it scatters again when it comes back through the neutron star. And then this happens over and over again until it reaches an orbit that's inside the neutron star. And then eventually it'll form a small region inside the neutron star that's actually quite small through repeated scattering. And this is a process that's called thermalization. What's happening is that eventually the dark matter reaches the same temperature as neutrons in the neutron star, which in the case of a neutron star, which is extremely dense, and for heavy enough dark matter, means that you can get a small thermalized ball of dark matter, which for instance would be about the size of a millimeter for PeV mass dark matter. And it'll become clear why I'm thinking about heavier dark matter in a moment, but this would be the case for even a quite hot neutron star. So for a really old neutron star, this would be an even smaller radius and an even smaller neutron star temperature, perhaps around 1,000 or 100 Kelvin. Okay, so after dark matter thermalizes into this small ball, you can think about it'll accumulate more and more dark matter over time, and then eventually the mass of the ball will become self-gravitating. And that's one condition you can place to roughly define when the dark matter would start collapsing under its own weight. You can also do a genes mass analysis where you look at the sound speed of the dark matter and you'll find a very similar answer. But if you require that the density of dark matter in that ball exceeds the neutron star density, this is one way to ensure that it will begin collapsing. You can then go do detailed calculations to make sure it can lose enough energy to become arbitrarily small. And then you need to also make sure that it could exceed its own degeneracy pressure. So for instance, if I think about fermionic dark matter, mass Planck cubed over mass of the dark matter squared would be the rough estimate for the Chandra-Sekhar mass of that kind of dark matter model, or would tell me how much dark matter I need to collect in order to form a black hole despite fermion degeneracy pressure. So that turns out to be 10 to the minus 12 solar masses for PV mass dark matter. So the kind of dark matter that can form these small black holes, which we'll see are going to implode the pulsars, can be KV to PV bosonic dark matter, although there are a lot of model considerations for bosons. So we're not going to think about that here. Instead, what we're going to think about is PeV to EeV, or very, very heavy asymmetric dark matter. Okay, so dark matter is captured, it thermalizes, it can collapse and form a black hole, and then that black hole could grow to consume the neutron star, although that's not a given. So there are a number of different pieces that you need to think about after you form the small black hole. One of them is bond accretion of the neutron star fluid onto the small black hole at its center that you formed. One of them is Hawking radiation. And then another piece that I started putting in when I started writing about this in 2013, after Chris Kavaris and others like Catherine Zurich and Haibo Yu had written some papers about bosonic asymmetric dark matter, is it turns out that the actual dark matter capture rate from dark matter coming into the neutron star onto the black hole can also affect the growth of the small black hole that you formed. But once you've done all those calculations carefully, you can convince yourself that there's ample parameter space where dark matter, which hasn't been detected by direct detection experiments, could form a small black hole inside of a neutron star, which then grows to consume the neutron star. And just I've blanked out here some new searches for this kind of phenomenon and just shown you the current bound. So this is from an old Milky Way pulsar. And actually it's confirmed by looking at a few different pulsars and confirming their ages, which are billions of years old. You can already set a bound on asymmetric dark matter with cross-section shown here, which is much below the current or future direct detection bounds at high dark matter masses. At low enough dark matter masses, you just never exceed the Chandrasekhar mass, so you never actually collect enough dark matter to form a black hole. At high enough dark matter masses, the black hole you form will be so small that it'll evaporate away very quickly via Hawking radiation. Okay, so that's the end of my quick expose of dark matter that both heats neutron stars, and then asymmetric dark matter, which can, at very high masses, for instance, for fermionic dark matter, collapse and form a small black hole and eat up neutron stars. And there's a lot of phenomenology we could talk about searching for this sort of dark matter converting neutron stars into black holes, but we're going to push on to think about dark matter in white dwarfs. And so if we've been looking at this parameter space here in green, next we'll see that supernovae, in particular type 1a supernovae triggered by asymmetric dark matter, can give you an additional probe of dark matter in this sort of giant plot of dark matter nucleon scattering cross sections versus masses. All right, so let's get into that. So before I get into that, I just need to review something which to a lot of the nuclear experts here will be secondhand at this point, and that is that a type 1a supernova is a kind of supernova that we've seen, which occurs when a portion of white dwarf material becomes sufficiently hot. There are a number of ideas for how this occurs in nature for the type 1a supernovae we see. And here, this is just a paper from 2013 that did some simulations and just showed the development of the nuclear burning flame front that swept through the star before it exploded. They looked at a bunch of different models for ignition points and white dwarf compositions to try to model a variety of light curves that have been seen. When I think about connections between dark matter and white dwarfs, it turns out that in a number of papers, which I wrote the first of, I think in 2015, is identified that dark matter, which forms sort of a core that collapses and can heat up the white dwarf through collapsing, can ignite a white dwarf and cause a type 1a supernovae. At the same time, another group of researchers thought about models where the dark matter passing through the star heats up a small region of the star and also causes ignition. And I would say these are the two primary methods people have thought about when they think about how dark matter could cause a white dwarf to explode. So I'm going to think about just the first one. So that's the case where dark matter again collects into a small thermalized core inside of, in this case, instead of a neutron star, a white dwarf. It eventually becomes heavy enough that it collapses. This will again have the same harmonic oscillator potential that the dark matter inside a neutron star has. It's just that the potential will be a little bit less, so that this will be a slightly fluffier ball of dark matter inside the white dwarf. And it turns out that within the lifetime of the universe, for a lot of dark matter parameter space, you can find that dark matter will collapse inside of the white dwarf, and that the heating that would be injected just through dark matter nuclear interactions inside the white dwarf is enough to ignite a type 1a supernova. When you think about what sorts of white dwarfs this would occur in, the fastest. It turns out it's the heaviest white dwarfs for two reasons. One is the obvious reason: the heavier white dwarf will have a larger gravitational potential and collect more dark matter. Another slightly less obvious but fun reason is that the more massive white dwarf is more compact. And so it creates a smaller ball of dark matter inside the white dwarf, or a smaller thermalization region. So you can build up a larger density of dark matter faster than the heavier white dwarfs. And so this is a plot from a paper in 2015 where I say for a variety of different white dwarf masses and radii, which just set using standard TOV type treatments, and densities for dark matter nucleon scattering cross-section showed here on the y-axis, and dark matter mass on the x-axis, and a fixed white dwarf temperature, just for simplicity. What is the required cross-section mass for the white dwarf to have a dark matter core collapse in its interior after 5 billion years for the red line, or 500 million years for these blue lines? And so the heavier white dwarf is the solid line, and so you can see that happens for the smallest dark matter nucleon scattering cross section. And so to compute the ignition, or whether or not the white dwarf ignites, we're using some standard results from Timms and Woosley, which established how much white dwarf material you have to raise to a critical temperature in order to ignite a flame front and get an explosion to start. And when I put in that constraint and I keep things very simple like I did in this first analysis, this is the relevant dark matter nucleon scattering cross-section and mass parameter space that I found for this process to occur. So using all of that, we can think about a number of different things. One thing we can think about is whether or not these sorts of processes could already be showing up in data. And that may seem like a little bit of a wild notion. And of course, all these dark matter things can be a little bit wild sometimes. But there is a little bit of a puzzle right now in the white dwarf explosions or type 1a literature. And that is that the progenitors of white dwarfs are sort of not as yet settled topic. So there are a lot of ideas for what are causing type 1a supernovae, like white dwarf mergers, accretion of a helium shell that then ignites the white dwarf. These are all things that people who study type 1as and white dwarf progenitors talk a lot about. But one sort of data set that sort of sparked a lot of interest in what's actually causing white dwarfs, or what the actual progenitor is exemplified in this plot. And that is that recent studies of low redshift supernovae and sort of models of burning of 56 nickel and 56 cobalt after the white dwarf explosion seem to indicate that there's a variety of progenitor white dwarf masses in the data sets we're using when we think about type 1a supernovae. So this classic notion that all type 1a supernovae, or all white dwarf supernovae, come from a white dwarf that becomes critical when it reaches 1.4 solar masses is not quite supported by the data anymore. And so their idea is that maybe the criticality ignition is what's occurring for high mass, maybe not, maybe it's all through a different pathway. But there nevertheless seems to be a variety of progenitors, or at the very least, there's some sort of progenitor that isn't just a 1.4 solar mass accretion. So in the dark matter world, what we can do is we can say we can see certain old white dwarfs. In this case, we can set a bound using an old white dwarf in the Montreal white dwarf database. And here you can see a comparison of where the bound sits with respect to neutron star implosions. So at low masses, it does a little bit better. And then at high masses, it can also do a little bit better. It turns out that the detailed phenomenology of what's going on with dark matter inside the white dwarf gets richer than in the neutron star implosions case. And here's why. For this region here, which I already showed you, dark matter does just self-gravitate and then heat up the white dwarf and cause it to explode. And so that's what's setting the bound over here. But it turns out that, of course, we can also think about the dark matter forming a small black hole inside of a white dwarf. And for the white dwarf we found, this constrains this parameter space. But then we can also think about the black hole even evaporating, and that evaporation actually causing the white dwarf to explode. And that sort of rules out a really tiny corner of parameter space, which I think has actually been superseded at this point by direct detection experiments. Okay, so that brings me to the end of some old stuff. And for the last few minutes of my talk today, I'll talk to you about some new stuff. So one additional thing that we've been looking into, which connects dark matter that would collect in white dwarfs, which would that can collapse inside of them and give you type 1a supernovae, is thinking about what effect those supernovae might have on galactic structure. But before I talk about that, I'm going to take a pause and just talk about, in general, how supernovae affect galactic structure. And just for you really quickly, what's sometimes called baryonic feedback. Although baryonic feedback is a broader term, but this would be a supernova-specific baryonic feedback. And then the idea goes back to Ponson and Governado in like 2011. And famously, this is sort of one way you can get a coring of your dark matter density inside the centers of galaxy. And by coring, we mean that the density at the centers of galaxy can be flatter as you move towards the center of the galaxy than you expect from an NFW or just a n-body simulation of the halo, which shows a pretty steep inner profile. And so there have been observations of cored inner profiles. And it turns out that galaxy modeling people have known for a while that supernova feedback can give you that sort of an effect. And here's how. So what happens is supernova and galaxies form after stars form from gas falling in and getting denser. So you'll get some population of supernovae going off. And when the supernovae go off, they'll inject a bunch of energy into the gas, and so the gas will puff out. And so the classic Ponson and Governado exposition of this said, okay, so if you cause the gas to puff out very quickly, and if that gas forms a substantial amount of the gravitational potential of your galaxy, then if I think about a test particle on an orbit inside my galaxy, then if the potential suddenly gets a lot softer, then I can think about the particles that are sort of on the exterior part of their orbits getting blown out in the process of that potential softening. Or I have some particle that's right at the edge of my halo, and then suddenly the potential is even smaller, and so that ends up on a wider orbit. Then as the gas recollapses, if it recollapses fast enough, a substantial portion of those particles will remain on wider orbits. So what's really happening, if you want to think about where the energy is going, is that the supernovae are, in essence, blowing out the dark matter particles by softening the gas potential in the galaxy. And so they showed in simulations, and lots of follow-on work has shown that you can get coring of your galactic center density in a lot of dwarf size and even larger galaxies. So this is a distance from the galactic center, and this is density in the galaxy through this sort of baryonic feedback effect. And so with grad student Ilda Buktuchin, who's gotten really good at running a galaxy simulation code called Gizmo, what we did was we implemented not just the core collapse supernova feedback that people typically put in, along with, there is actually a type 1a feedback, although it's very rudimentary, but we also implemented dark matter induced supernovae. And what's sort of special or interesting about this is that the dark matter induced supernovae will tend to occur preferentially towards the center of galaxies. And that's because there's more dark matter there. So if you have white dwarfs forming at the center of your galaxy, those actually will tend to blow up faster in models where dark matter even causes a small fraction at the highest densities of your white dwarfs to blow up. And just to show you a bit of a difference that we'd expect for the dark matter induced feedback here on the right versus the typical core collapse or other supernova feedback here on the left. So the core collapse feedback here shown on the left is going to mostly be the same throughout the galaxy. And as this feedback goes on, we expect this feedback to remain basically the same as the galaxy evolves. For dark matter induced feedback, it's a little bit different, and it's kind of fun because baryonic feedback is already quite a nonlinear process. but this actually is something that becomes, excuse me, I'm just going to fix the zoom on this really quick to get that back up to frame. This is actually something that's going to be even more nonlinear, because what I'm going to get is as baryonic feedback progresses, I'll have less dark matter at the center of my galaxies, which means I actually get less baryonic feedback occurring from dark matter processes over time. Or that's an expectation we had going in that we've seen borne out in simulations. So here, what I'm showing you is for a galaxy which we simulated with 10 to the 9 solar masses worth of material, which is a typical dwarf-sized galaxy and actually matches the Ponson and Governado result. And for a dark matter mass fraction and gas mass fraction that also match what you put in for a typical dwarf galaxy. We can look at for dark matter parameters where the dark matter cross-section is really high here in blue, is intermediate in green. So this is a cross-section that's not really ruled out yet. And then is actually quite small here in yellow. What is going on with respect to number of white dwarf supernovae? So here we're seeing that at lowest dark matter cross-section, there's just no white dwarf supernovae because it's just not happening. At an intermediate cross-section, we're getting some white dwarf supernovae, preferentially towards the center of the galaxy, I should add. And then for the highest cross-section, we're just getting tons of these white dwarf supernovae going off very quickly. But a lot of linearities that we didn't even quite think about when we started out actually creep in, because what we found is that for reasonable dark matter parameters, you actually can even affect the amount of stellar mass formed by blowing out so much gas that, oh, okay. So I'm getting questions in the chat. So I'll respond to those in 1 second, but I'll just finish what I was saying. What we're finding is that you can actually quench star formation, that you can actually inject so much energy that you actually form fewer stars than you would without these sort of dark matter induced supernovae. So let me go to the questions really quick. Okay, I thought supernovas were mostly driven by neutrinos when Chandrasekhar core collapse forces electrons. How dark matter could drive a supernova explosion. Right. So the kind of supernova you're thinking about there are core collapse supernovas. And there you're thinking about like how the energy is causing the core collapse supernova to explode. But for a type 1a supernova, those go off as a result of nuclear energy. So that results from carbon and oxygen burning inside of a white dwarf. And so that's the sense in which dark matter could heat a small region, and then that sort of ignites a thermonuclear flame front that sweeps through the white dwarf and blows up the rest of it. So that's sort of the difference there. In a core collapse supernova, there's no latent energy in the same way that you're releasing. There, it's all the gravitational potential energy of a mostly iron core collapsing. And of course, the iron can't be fused up further, which is why it's collapsing. And then the second question, are type 1a supernovae observed to happen preferentially near the center of galaxies? That's a great question. So it's actually hard to do a study of that question itself, because we don't know to what extent our observations of type 1a at the center of galaxies are occluded or are not being seen, because we don't really understand gas density and how it sort of impacts the observation of type 1a light curves towards the centers of galaxies. At the moment, there was one group that tried to do a study on that, and then they ended up pulling it after a little while. And I could talk to you about that offline. But actually, you can't even find it on the archive anymore. It's really hard to get the data right on that, but it is something that we have pursued as well. Okay, great. And so then, let me see. So then the last plot I'll show you is that for different dark matter cross-section parameters shown here, you can actually get different coring of galaxies. And so we're studying this further. We're first going to show some results. We're going to put out a paper where we just show dark matter induced baryonic feedback. And then from there, we'd like to think about applying that to a fuller cosmological simulation and see if we feel confident enough about what the dark matter does versus what a universe without this sort of dark matter would do to say whether or not we think there's a dividing line and a sort of bound on the relevant parameter space. One complication with setting a bound using this sort of a study that has definitely come up is that it's a really nonlinear effect. So this green line here is the intermediate cross-section I was showing you about. which is actually causing more coring than either the really small cross-section here, which is just through random variations close enough to this orange one, but not exactly on top of it. And then here's the green one here, which we're seeing is giving the most coring. But then if I really ramp up the cross-section, what I find is that that actually doesn't give me as much coring. And that's because I've shut off stellar feedback. So we have some ideas for how we might look at particular galaxy properties, maybe to study this sort of effect further. But I'm a little bit over time, so for the moment, I'll stop there. There's another question in the chat that I'll answer in a second. And just say, I've talked to you today about dark matter heating neutron stars, asymmetric dark matter that can cause neutron stars to implode, and white dwarf explosions from asymmetric dark matter through a similar sort of core collapse scenario, but inside of a white dwarf, and connections to type 1a supernovae and galactic structure. And so that's it for my 30 minutes, which went over to about 35. Sorry about that, but thank you, everyone.
Great. Thank you so much, Joe. And so we do have, one question already. If you have additional questions, folks, please virtually raise your hand and we'll call on folks. So Andreas, if you'd like to unmute yourself and ask your question maybe in more detail, go ahead, please.
Yeah, well, this question, I think it is related to one of the previous questions that was asked. How do you imagine the collapse of the dark matter core heating the white dwarf matter? How do you transfer the energy from the dark matter to the baryonic matter inside the white dwarf?
Yeah. So what's nice here is it's all a self-contained model, or at least the parameter space is quite simple. So the same dark matter nucleon scattering cross-section that is assumed to capture the dark matter into the white dwarf turns out to be efficient enough at transferring energy from the collapsing ball of dark matter to the white dwarf. Or to put this a little bit differently with a slightly more complicated plot, this line here, this dotted line here, shows you as a function of the dark matter mass here, how large I have to make the dark matter nucleon scattering cross-section so that I'm transferring energy from the collapsing ball of dark matter into the white dwarf material fast enough that it raises the temperature of the white dwarf to the ignition temperature, which is about 10 to the 10 Kelvin, or about a mega electron volt if you like natural units. And so the answer, what's transferring the energy, it is just this nucleon scattering cross-section between the dark matter and a nucleus. So you have this ball of, yeah.
This is like free fall collapse? Or
you could think of it as starting out as free fall collapse, yeah, but then it would be a collapse where it would sort of be a balance between free fall and the scattering dark matter transferring the energy. So it essentially collapses as quickly as it can transfer the energy. Otherwise, they are kind of in free fall. And then a question you could ask is it an isothermal ball of dark matter as it's collapsing, or is it going to be something where there's like a gradient of temperatures that's larger towards the center? And that depends on the dark matter self-interaction cross-section. But in either case, it actually doesn't really change the answer substantially for whether or not the white dwarf ignites, because what really matters is just how quickly you're transferring the energy to the white dwarf.
Okay, thanks.
Yep.
I see a hand from David. The floor is yours.
Hello, can you hear me?
Hi. Yes,
Okay.
I can.
Yeah, I'm the one who asked about the Chandrasekhar forcing about how the supernovae are driven by neutrinos. And I admit I am not an expert, you are, but I am confused. The thing that makes SN1As, the perfect distance candles, is uniformity of their process. At the very instant the external source of matter falling on the white dwarf hits the Chandrasekhar mass, you get a uniform type of supernova triggered, but their interiors are not uniform. There are all sorts of chemical things still going on in there. And now you seem to be saying that it is nuclear reactions among atoms that are still atomic that drive that kind of supernova as opposed to a core collapse. And yet, of course, the fact that it's when they hit the Chandrasekhar limit that if the collapse happens, that implies that it's similar to the core collapse. So if it's just nuclear reactions, I don't see where it would get the power and where it would have the uniformity that we rely on in order to be a distance candle. I understand that I am ignorant. I'm just simply expressing my ignorance.
Yeah, so let me unpack that a little bit and just tell you what I think the type 1A experts, who I wouldn't necessarily count myself among, but of course I've had to read a lot about this and work with it over the last decade, where they would, what one of them I think might answer with. And I'll try to delineate what I think is controversial and uncontroversial. So what I think is uncontroversial is that there's a story where the mass number inside the white dwarf does start at a low mass number, 14 to 20. It can be carbon and oxygen, or it can be carbon and oxygen with some neon in it. That carbon oxygen neon mix will fuse, and it's supposed to fuse a substantial fraction, like about half at least, of the white dwarf, up to 56 nickel, which decays to 56 cobalt, which decays to 56 iron, which is going to power the type 1A supernova light curve, which looks a bit different than a core collapse light curve. This is uncontroversial. That's where type 1As come from. Now, what ignites the type 1A supernova? What starts the nuclear burning inside the type 1A supernova? What causes the carbon, the oxygen, the neon to fuse? That is an open question. And for the best review of that, I'm definitely going to, I would definitely start you on like the Dan Maus et al. Review. And you'll see that the name of the review is the type 1A progenitor problem. What actually started a type 1A supernova? And there is a persistent lore in the literature that yes, type 1As are great standard candles because they're all starting the same way. You start with a 1.4 solar mass white dwarf, then it accretes a little bit more, and that means that it's at this critical mass, and then something happens, it ignites, it explodes. The thermonuclear flame front sweeps through it, it explodes, and that's your type 1A supernova. Type 1A people don't really believe in that lore anymore. In fact, type 1A light curves are not perfectly uniform. The solid lines here are models, but these dotted lines are actually observations. And what you can see is there is quite a bit of variation in the peak luminosity of these light curves. And there's even variation in what's supposed to be uniform across all of them, which is the stretch to max luminosity relation, which is sometimes called the Phillips relation. Even that, there is non-uniformity in. So if you go to look at type 1A fits, so when people are trying to measure what they measure to get lambda, or the measurement for dark energy in our universe, they're using all sorts of factors, including recently even things like what the metallicity is in the host galaxy, to study how these light curves vary. And that's partly part of this, and this actually isn't that controversial anymore, that we're seeing type 1A supernovae from a variety of progenitor masses, all the way from 0.8 solar masses up to 1.4 solar masses, and then some super luminous ones, which, if you're asking me, are probably the merger of white dwarfs that are, like if you have 1.8 and 1.8 solar mass white dwarf and they merge, then you'll get a 1.6 solar mass progenitor, something like that. And so you can see here, just with the best modeling they had, there's quite a variety of progenitor masses. And so the progenitor pathways that aren't dark matter, which I definitely will emphasize, since we always like to link astrophysics and dark matter, but there can only be one correct dark matter model, and astrophysics is probably coming into play. So the progenitor things that don't involve dark matter are like white dwarf mergers. So maybe just low mass white dwarfs merge a lot, and that's what's giving us these lower mass things. And in merging, they cause that thermonuclear burning to begin. Then, some sort of tunneling thing at the center of lone white dwarfs that kind of just occurs randomly, where, you have some sort of piconuclear reaction. That's something that people look into. And then you can even think about, and these are disfavored by simulations and a lot of arguments in literature, and this is all something that people, I think, can reasonably debate. People think about like accreting, for instance, something like a helium shell in the white dwarf, and then that being ignited. That's been studied, and that wouldn't necessarily need to happen for like a 1.4 solar mass white dwarf. It could happen for a lower solar mass white dwarf, and that could compress the white dwarf. There's debate over whether that actually works, but that's another idea for what the progenitor could be. But yeah, so I hope I've unpacked that a little bit. So I think thermonuclear burning being the source of the thing powering the type 1As, I think there's enough energy there because you're still going to have MeV to 10 MeV per nucleus if your carbon burning is efficient enough. And so that's enough to blow this thing apart and give you on the order of 10 to the 52, 10 to the 53 ergs, which is also what you get for a core collapse supernova. But yeah, the exact type 1A progenitor, I think it's fair to say it's still an open problem. What exactly is causing the vast majority of these? And I think even based on the type 1A light curves we're seeing, there will be a few progenitors. So I don't like to get this to make this too messy, but there are even different kinds of type 1As. So there's the standard type 1As, which you'll put in your data set if you're looking for dark energy. Then there's something called a type 1A X supernova. And if you ask me or me talking to experts who know better than me, a lot of people think type 1A X supernova are probably the kinds of supernova that follow the traditional story where you accrete to 1.4 solar masses. And the thing about type 1A X supernova is they have a lot of lines in them that you'd expect to see if there's like a messy accretion disk around the type 1A progenitor. I'll stop there. There are other kinds of type 1A supernovae as well that are a little bit mysterious. Some of them occurring very far away from galaxies, something called calcium gap transients. Yeah.
Well, thanks. You just made my theology a whole lot more complicated.
Yeah, sorry about that.
Do we have any more questions for Joe? I don't see any more hands, so let's thank our speaker again.
Thank you, Joe.